Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Okay, module 2, setting up deep forecasting environment, part 2. So this is the one that we're going to do some basic time series operations in Python. So if you haven't watched part 1, I highly encourage you to start with that. This is where we talked about different packages that we're going to use for the course. We also covered some prereqs for the course. And we also discussed why we are using and what we're doing in this course based on some Kaggle survey data, right? We said Python is the most popular one, and then a combination of Jupyter Notebook and VsCode. And then we talked about, if you wanted different packages in Python, and if you want to run things locally on your computer or on a Google Colab. Either way, you should be set for the course. And now let's dive into the Python part. Okay, so let's actually go to the GitHub folder. So here's the deep forecasting. If you go to my account, deep forecasting, lectures and codes, module 2, here's the notebook that we're going to work with, right? And I already told you that you can run it either in Google Colab or you can run it on your local computer. So the cool thing is that if you want to do it in Colab, just go ahead and click on this open in Colab. And then it will actually, let me go back and open a new window. It will send you to your Google account. So depending on what account you're logged in, and then you just need to go ahead and connect. So you don't, for this notebook, you don't need to use any special hardware like GPUs. You just connect it to your normal CPU, and then you're all set. So literally you don't need anything else in terms of running your code. You can just follow along. You can make a copy. You can go ahead and make a copy for yourself, say to copy to your own drive. And the thing is that this is running from my GitHub now. So that means if you go ahead and press run, it's going to start complaining or giving you a warning that, hey, this is, let me actually show you. It says that this notebook was not authored by Google. Do you trust it? You can say, okay, go ahead and run it anyways. And the other thing is that if you make changes to this one, you cannot save it. So I encourage you to copy to your own drive and then try to play around with it there. So again, if you want to run things on Google Colab, you're literally set to go. And then that's it. You can go ahead and run the codes line by line. And one other thing I need to mention is that maybe the only downside of working with Google Colab is if you want to do PyCaret, every single time that you want to run your code, you have to run it. You have to install the PyCaret, right? So basically, or maybe different other packages that you need to work with them, right? So for example, in this notebook, we're going to work with PyCaret and Yahoo Finance. So because this is not pre-built in Google Colab, you have to do it manually, right? So for example, you can go ahead and do pip install PyCaret, and if you want to install the full version, you have to do pip install full version of that, right? For this notebook, we're going to work with the light version. So if you want to run things on Google Colab, make sure you install PyCaret and you also install, let's say, Yahoo Finance, right? So if I run this line, so this is going to take a couple of minutes depending on your speed connection. And yeah, so I'm gonna let this run. I'll go back to the notebook and run these things in my local computer. And yeah, here's the topics that we're gonna cover today. So let me go back. So this is what I want to open on my local computer. So I assume that you have cloned this repository. Now you have a folder on your local computer, and then you can go ahead and open your VsCode. So this is my VsCode. So actually I went ahead and opened my GitHub folder by pressing this one. And this is the entire GitHub folder that we have. Remember, let me actually share. So these are all the modules, and you're going to go to module 2. There's a Python crash course, and this is what we're focusing on. Module 2, time series basics. So this is the exact same file that I just showed you over Google Colab. I can click on this one here and open another Colab as well. All right, so, but here before me doing it on my local computer, I just want to make sure that you have created your own environment, you set up the PyCaret in it, and all the packages that you need, right? So again, if you are doing it in Google Colab, you can pause the video and then, or maybe you can jump to the next section. But if you want to run things locally, just stay with me. So let me see. Yeah, this is already, there you go. So this maybe it took less than a couple of minutes to install PyCaret and Yahoo Finance. Yahoo Finance is just 10 seconds. PyCaret is a bulky one. And that's what we need. So that means that next time, if I close this thing or if I just shut it down, if I want to run it again, I have to install this thing. So maybe this is the only downside for our course at least, when we want to work with Google Colab. Other than that, this is pretty straightforward. And the cool thing is that even the deep learning packages like Keras is already built in, so you don't need to install any other packages. So that should be cool. So if I can go ahead and say, okay, import it and run the rest of the notebook, right? Now, if you want to run things locally, let me actually help you setting up your environment. So this is my environment up and running. So I have a PyCaret kernel, but on your computer, you don't see something like this. So let's set it up together. So I assume that you have installed Anaconda, and I want you to go ahead and open Anaconda prompt. So Anaconda prompt, right? So this is your Anaconda prompt, and you can see right now this is in your base environment. So we don't want to install PyCaret on our base environment because we don't want to mess this base environment with that bulky packages, right? We want to keep our projects separate from each other. So for example, if I do conda env list, it's going to give me a list of my environment on this local computer. And for example, I have finance, meta, profit, PyCaret, TensorFlow GPU, something for web browsing, and etc. So as you can see, I keep these environments separate from each other. So let's go ahead and create an environment together for this course. You can call it whatever. I can go ahead and call it, for example, let's say deep forecasting, right? You can call it whatever. So I'm going to say conda create, and we need to do a flag of, it can be name, or you can write name or just n. You can give it a name, right? So let's call it deep forecasting. So I'm going to call it deep forecasting, and the Python that I want to install is going to be Python version 3.11 because this is the latest version, both in Anaconda and the PyCaret. So I'm going to stick to that one. So we're going to create an environment called deep forecasting, and we're installing Python 3.11, and let's go ahead and create this. Okay, so this is going to take a little time, and then it's going to install these packages for you. Say yes. And yeah, and then I'm going to go ahead. So now it seems that this environment has been created. Let's go ahead and check it out. I'm going to do conda env list again. So now the deep forecasting must be there. Let me actually go ahead and close this thing, because make sure your VsCode is closed, and then you create this environment, and then if you open your VsCode again, it should pick up that environment, right? If not, you have to manually give it the path, right? So then let's go ahead and activate this environment. Activate, well, we have to do conda activate. Conda activate, what did we call it? We call it deep forecasting. Okay, so now we are in the deep forecasting environment. So if I simply go ahead and say conda list, these are the list of packages that are already installed, right? So already these are installed here, and right now these are the very base packages that comes with Python 3.11, right? I can, for example, do pip install Yahoo Finance. So pip install Y Finance. And then this is going to basically install that package for me. And the good thing is that this is only, you need to install it once. It's not like Google Colab that you have to install it every single time. So it's going to install it once, and then later on you're going to use this environment and then run your code on it, right? So now if I do again conda list, Yahoo Finance must be there, as you can see. And of course, some other dependencies were also added. And then your last task is to do something like this. You have to do pip install. Again, if going back to, let me pull up this PDF one more time. Where is our PyCaret? installation. There you go. So remember, for PyCaret, we need to do pip install PyCaret full if you want to get the full version of that, right? So I go back to my environments. Let's see, yeah, this one. I do pip install PyCaret and then bracket full. So this is going to take 5 to 10 minutes, again, depending on your speed connection. This is a bulky package, and then you can go ahead and press enter. Okay, so I'm going to let this run, but hopefully you will not get an error. So we will check on this later. But basically what I added, I created an environment called deep forecasting, and then I installed some packages, mainly the PyCaret. Inside the PyCaret, there's everything. You have scikit-learn, you have stats model, all the packages that we need for the course, for the first 2 sections of the course, econometric and machine learning model. All right, so I'm gonna let this run and go back to my VsCode. Now, if I go ahead and open my VsCode, then so right now, this file, when I double click on this, when I open it, this module 2 time series basics, the environment is PyCaret. If I click on it, I can go ahead and change it, change another PyCaret environment. And as you can see, deep forecasting is here now. So it was automatically added to your VsCode. This is what I just created. So right now, if I click on it, it cannot run the PyCaret because it hasn't been installed yet. It's working on it. And as you can see, it's still working on it. Again, this is a bulky package. But in your case, you should, after you have installed it, you should be good to go. I already have an environment. It's called PyCaret. So inside this PyCaret, I already have a bunch of other packages that I manually added, like Yahoo Finance and etc. So now I should be good to go. I'm ready to run this thing locally on my computer. So again, either you're running it on Google Colab or you want it locally, you're ready to follow along with the code. All right. So once this is done, I'm going to show you how to delete your environment as well. So once this is finished, again, this is going to take some time. I'm going to show you how to delete that environment. Okay. So time series basics in Python. For this notebook, I'm going to do it locally, and maybe for future notebooks, I'm going to run it on Google Colab. It really doesn't matter. First thing first, importing libraries. So you need to import your PyCaret. If it is Google Colab, run this. If it is not, do not run it locally. You only need to do it once. And I don't want you to do it through notebooks. Just do through Anaconda prompt. So one of these things that we just did, right? And let's go ahead and import. It should not complain. So because we already have Yahoo Finance, Matplotlib, Pandas, and NumPy. And let me actually show you what is inside my Anaconda. Just bear with me one more second. So this is my PyCaret environment. So if I do conda list, it's going to give me the list of all the packages in my PyCaret, right? So here's the list. And as you can see, I also installed Yahoo Finance. So XGBoost is there are many packages. And stats model, where's this? Yes, stats model, scikit-learn, you name it. So all these models, yes, scikit-learn are here. So the whole point is that once you install it, you're pretty much set. You don't need to install any other packages for the course, except for the deep learning section, which we need to do TensorFlow cares. All right, so now let's run the rest of the code. So this is going to be some basic time series operations in Python. This is different from the Python crash course. So this is specifically designed for the course. All right, so let's ignore the warnings. We're going to work with 2 data sets. So one is airline passenger data set. This is a monthly number of passengers from 1949 to 1960. And the other one is Apple stock data set. We're going to collect the close price from, I think, December. I did it December 2021 or 2 until today, which is summer 2024. All right, so we're going to use Yahoo Finance. And remember, from module 1 in the theory lecture, we talked about it. Throughout the entire semester, we're going to work with these 2 time series. One of them is super well behaved, airline passengers. There's a clear trend. There's a clear seasonality. It is well behaved. We don't need super complex model to capture that relationship. The other one is on the other side. This is a stock price, which is the least well behaved. So if you learn how to handle these 2 extremes, you should be good to go for any time series which behaves something in between. All right, so let's go ahead and import that. So this is, I'm reading from my GitHub. No, this is my GitHub deforecasting. If you go to the data folder, there is this air passenger CSV. Let me show it to you where you can find it. So here, if you go to deforecasting, again, I assume that you have cloned this repository already. So, and we can go to data and air passenger. So this is the data, right? So basically, when I look at the raw version, this is where you can copy this URL and then paste it in your editor, and then say, okay, import this, read the CSV for me. And let me go back. So here's a data set, and as you can see, there are two columns: month and passengers. When I'm importing this thing, I want to directly set the month into index. Okay, so that's why I'm going to do index column month. And now I can look at the head of the data. So this is the index, month, and passenger. So that was your airline passenger data. So we call it AirPass. The other data set is our Apple. So I'm going to go ahead and use Yahoo Finance download. My ticker is Apple. Start day December 22nd. There's a reason I want to show you how we can handle the holidays, the market holidays. So that's why I wanted to do from December 22nd and until the 1st of May 2024, right? So let's go ahead and show the head of it. So this is Apple's stock price. Again, date by default is index. I didn't need to specify index column is equal to date. So by default, index is date. And these are the columns, open, high, low, close, adjusted, close, volume. So we're going to stick with close. So imagine this is what we want to predict. So typically we do adjusted close, but just for the sake of argument, for simplicity, I'm going to do close. And so we need to go ahead and create a new data frame. So that's why I'm using two brackets. So from Apple, give me the one column close. I do two brackets to make sure that this is a still data frame. And look at the head of it. So this is the data frame that I'm going to work with, Apple close, right? Now it's time. Let me actually go ahead and minimize this one. Okay. Now it's time to make sure that the time index is correct. Okay. So after importing the data set, we need to make sure that the index is correctly set to date time format, right? This is essential for performing time series analysis, as a date time index allows to leverage pandas, which is a powerful time series functionality, right? And of course, we need to make sure that it is compatible with PyCaret as well. So if I do airpass.index, so this is what I get. So something, going from 1949-01 January to December 1960. And as you can see, the date type is object, right? So if I pass something like this to PyCaret, it's going to complain. We may not need it for this notebook, but throughout the course, we will work with PyCaret, and then PyCaret is going to complain. And you have to go ahead and make sure that this frequency is specified, right? So that's why we need to convert the month column to date time we already converted to date time, but we need to set the period to month, right? So I'm going to say, take this index and just double check its date time. So change it to date time. And then off of that, just make sure the periodicity is monthly. And now if I run this, if I look at the data type, it's a monthly data, right? So this is different from this one. Okay. Now, if I pass this one to PyCaret, it's not going to complain, and it's again, the reason is that the author of the PyCaret wanted to make sure that your time index is correctly set up. So this is some compatibility issue. It may not be important when it comes to visualization, but for, again, handling time series with different packages, we need to make sure that it is consistent. So that's why maybe this is one of the most important steps in time series, working with time series in general. Make sure your time index is correctly set up and you have the right period for that. So right now this is monthly, we specified month. For the Apple stock, we imported something from Yahoo Finance. This is already in the correct format with the date column, and date column is going to be date time. However, we need to make sure that the frequency is specified, right? We need to set it to business days frequency and handle missing values by forward filling. So bear with me. Let me show you what do I mean by that. Actually, I can remind you what was the data set look like. So this is close price, right? December 22nd, $175.63, 23rd, and as you can see, 24th and 25th. 25th, of course, is basically Christmas, and then 24th is Christmas Eve, and the market is closed, so we don't have data for that, right? But it is a business day. So the way that we need to fix that, it says, okay, make sure, let me actually show you the index before making any manipulation. If I look at the Apple_close index and make sure it's datetime, you will see that the frequency is none. So we have to specify the frequency. Again, if I pass this to PyCaret, it's going to complain. So you have to specify the frequency. Many other packages as well. PyCaret is written on top of skate time. So if you want to do skate time, that one is going to complain too. So that means that you have to go ahead and change the frequency to business day, right? So I'm going to say this is Apple close index, and I'm going to change the frequency to business day. And now if I run this, comparing the frequency of this one to the previous one, this one is business day. All right, so far so good. So it means that we have, look at that, we have 22nd, 23rd, 24th, but wait a second, we didn't have data for 24th. Do you remember? So look at that, this is original data, 22nd, 23rd, and then 27th, because that was Christmas Eve. But if you specify business day, then you have some NA values and you have to fill them. So the method that we're going to use is forward fill. This is pretty straightforward because we're going to say, okay, today, I don't know, let's say it is Monday, and imagine the tomorrow market is closed. The market, the closing price for today is $100, and tomorrow is market holiday. What price should I use for tomorrow? It's going to be 100, right? So I'm going to forward fill it. So basically this means that whatever price was on 23rd, use it for 24th, because 24th was holiday. So that's what we call forward filling. So we're going to do fill NAs and then do forward fillings. And now let's look at the head. This should make perfect sense. So 22nd, 175.63, 23rd, 176.27. Now this is Christmas Eve, market is closed, the price is the same as the last day. All right. So now our both two data sets are ready to basically play around with, right? And actually, let me show you what we're going to do in a high level. So here's the outline, and I can show you the outline in the Google Notebook. Maybe it's clear here. Yeah. So this is what we're going to do. We are going to do some simple data exploration, and we're going to do some transformation, do log transformation, power transformation, boxcox. We will do some simple ACF, PACF plots. We talk about stationarity and maybe fixing it by doing simple differencing. We do seasonal decomposition. And finally, we're going to plot the benchmarks for our forecasting models. So we have one step ahead benchmarks and multi-step ahead or multi-horizon benchmark. So, and I have an exercise for you at the end of it. Okay, so let's go back. All right, so data exploration. So we need to just quickly see if there's any missing value. So I'm going to run this line. Basically, if there's any missing value, just print it out. There's no missing value for airline passenger and no missing value for our Apple stock price, because we just forward fill the missing values. And then we can look at some summary statistics. And just, again, if you want to see what is a naive forecaster, not naive forecaster, what is your simple average benchmark? For this data set is 280, for the other data set is 165. So this is your benchmark if you want to use a simple average model, right? And again, these are some simple statistics. You can see there are 144 observations from this time to this time. Frequency is month. And I'm simply looking at some simple information of all these data sets, right? And then for Apple stock, 615 days, and the frequency is business days. Okay. And then the next thing, obviously, we need to plot them. So here's a simple plot. And again, don't worry about well, actually, let me see what it's complaining. Did I not run? Yeah. Float are going to be strings, or real number, not period. Okay, let me go ahead and fix it. Actually, I'm glad that it is happening, because this is one of the most common issues when it comes to handling time series indices. And it's a compatibility issue, right? Let me actually show you the air pass air pass info. Oops, sorry. As you can, oh, not info. I just wanted to look into the index, right? As you can see, the index is period month, and this is what PyCaret needs to work with. PyCaret needs to work with periodic data, and you have to specify that period. But when it comes to pandas visualization, it is complaining. It is saying that it should be either a string or real number. So we need to convert it back. So there's this compatibility issue. Of course, I can use some simple plotting. You know, I can do air pass dot plot. This should work. Yeah, this shouldn't complain, right? But when I'm doing panda, it needs to be datetime, and now it's period. So you can fix it in many different ways, right? But the easiest way is to make sure that the air pass is, you know, you don't touch this periodicity, because when we're doing modeling, PyCaret needs that thing. So let's change it when it comes to plotting things, right? So I'm going to go ahead and add that index and change it back to, let's say, datetime, right? So I'm going to do air pass dot index. Well, this is my X. And this is Y. So Y, I can be more specific and say passengers. So let's see, passengers. And then this index needs to be changed to timestamp. So this should work now. Okay, so as you can see, I added the index manually and changed it back to datetime by doing timestamp. And now I'm saying this is my X. This is my Y. Okay. All right. Hopefully it makes sense. Again, these compatibility issues at the beginning, it's going to be kind of annoying, especially if you are beginner in time series visualization and handling indices. But as I said earlier, this is one of the most important steps that you should become quite familiar with when you're doing time series analysis. And again, don't worry about it. You know, if you ask a simple question from ChatGPT or Google Gemini, it's going to help you set that up. And yeah, so let's keep going. Let me go ahead and save this and keep going. All right, now let's do the same plot for Apple stock. So for Apple stock, for this one, it seems that we didn't need to do that because, again, the index was different. If you get the same error, you need to go ahead and fix it. So the frequency for that was daily, and the way that Yahoo Finance is handling that index was different than what we did manually. All right, so this is Apple stock price. And as you can see, this is a super well-behaved data. This is unbelievably not well-behaved data set, stock price. All right, now let's do some data transformation. So the next step is to we visualize things, we hopefully clean the data, get rid of the missing values or interpolate them. Now let's do some data transformation. Why did we do that, and why do we care? So to simplify the pattern in historical data and make them more consistent across the entire data set, we will apply various mathematical transformation, both to airline passenger data and Apple stock. So here I'm going to visualize the airline passenger data. Transformation, here's the point of transformation. It can help in stabilizing the variance and making the data more suitable for modeling, right? So look at that. It seems that, yeah, the seasonality is here. It goes up and down, but the variance is increasing. This makes sense, right? And let's say we have heteroscedasticity here. The variance is increasing. How can I shrink that increase in variance? If I do a simple log transformation, it's going to do the job for me, right? So again, one way is doing log transformation. There are different ways of transformation, namely log transformation, power transformation, and cox-mox or boxcox. So I'm going to do all of them here. So it is important to note that these transformations can significantly change the interpretation of the data because, and you should use it with caution, right? And we will try multiple transformation and compare the results to determine which is most appropriate for our data. And okay, so let's go ahead and start with the log transformation. Again, it helps to stabilize the variance of time series data. And as you can guess, if you're doing long-term forecasting, you don't need to be worried about that increase in variance if the log transformation is taking care of that, right? Don't worry about the details here. When we get to the theory part of the next modules, in the right time, I will explain these things in more details, but these are some general time series operation, general time series concepts that we need to be aware of when we're doing Python. Okay, so log transformation is pretty straightforward. I'm going to add a new column, call it log passengers, and this is from numpy package, numpy log, pass the passengers. Okay, so this is the log of that. We can print the head of it to see the actual passengers and log passengers, and on top of that, we're going to plot it. And again, for error passengers, I have to fix this index to timestamp. This is just for visualization purposes. We're not changing the error pass index type, which is period. Okay, so there you go. This is passengers, log passengers, and as you can see, this is kind of, the variance is kind of constant. So this is perfect, right? If anything, if I don't want to do anything fancy before doing a simple, let's say, traditional or classical econometric model, I will do a log transformation because it seems that it is working, at least visually, perfectly here. It's handling the increase in variance, right? Another type of transformation is called power transformation. This is simply, as the name suggests, something to the power of another thing, right? Typically, we can do square root, power of to the power of 0.5 or 1/2. It can help to stabilize the variance and making the data more normally distributed. Again, this is another version. I'm going to go ahead and create another column called square root, and simply from numpy square root, and then do the visualization. There you go. I'm going to plot them all side by side so you can compare. So this is also, it seems that the variance is still increasing, but it's not as exaggerated as not doing this transformation. So maybe log transformation was better. And of course, the best of all is boxcox transformation, which is a combination of two, right? So this is more flexible, that can handle a wide range of data distributions. It requires all values to be positive, which our dataset already satisfies, right? Now, there are versions of boxcox transformation that can handle negative values. So there's going to be a negative sign. So the formula is slightly different, but basically it's going to slightly be different here. But basically the gist of it is the same. So we have two functions here. If lambda is basically our transformation parameter. If lambda is equal to 0, it's simply log transformation. If lambda is anything different from 0, it's going to be power transformation, right? So this is simple power transformation, y to the power of something divided by some constant, right? All right, so again, the transformation parameter determines the nature of the transformation. If lambda is equal to 1, go ahead and use it. Y to the power of 1, which is y minus 1 divided by 1. So it's y minus 1. So basically your new data is like the previous one minus 1. It's exactly the same, right? And there's no transformation there. Data remains unchanged. If lambda is equal to 0, log transformation. If lambda is equal to 0.5, this is our square root transformation or power transformation. And of course, you are wondering, so why are we doing this? Because we can back out this lambda. We can find the optimal lambda that is maximizing the likelihood, right? So, and how do we do that? This is, let's call it optimized lambda. We're going to use SciPy package. It provides a method to find the optimal value of lambda that maximizes the log likelihood function of the transform data. So what does it mean? It means that the transform data is as close as to normal distribution as possible. We are maximizing the likelihood of that thing to happen. So obviously it helps to stabilize the variance. This is done using boxcox function, which returns both the transform data and the optimal lambda. So let's do it. Actually, I'm going to do it manually first. This is just for the sake of visualization, and then later on we're going to do we're going to import boxcox from SciPy. If you want to do it manually, so this is a function that I put together, and basically this is with the help of ChatGPT. Again, I didn't mind just asking ChatGPT to write it for me. And for coding like this, it's not worth to reinvent the wheel from scratch, because it's already there. You can leverage that. So we are saying, let's create this function, right? So I have if function. If lambda is equal to 0, do this. If it is not equal to 0, do that, right? So this is basically what I'm creating. If lambda is equal to 0, your transform data is simply log. If it is not equal to 0, it's data to the power of lambda minus 1 divided by lambda. This is exactly the formula we use. So if you want to do it manually, I am creating a function that is taking data and different values of lambda, right? Just for visualization. You can simply use this part, which is one line of code, right? For visualization, I did it manually, and then I'm trying it for 3 different values of lambda and then visualize it, right? So So here it seems that when lambda is equal to, remember lambda is equal to 0, going back, it is a log transformation. If lambda is equal to 1, do we have 1 here? Well, actually, I can go ahead and add. Well, if I add 1, the scale is different. It's going to give me the original data, so that's why I don't want to do 1. I do 0.1 and minus 0.1, so these are different transformation. Again, just to show you, if I do 1 here, this is going to give me the original data. So this is original data. All right, so that's basically for different values of lambda, we're getting different things. What is the optimal lambda? The optimal lambda is that makes this distribution, the distribution of the data as normally as possible. So we don't need to do that optimization manually. We can go ahead and use boxcox function from SciPy stats module. So I'm going to say create a new column, call it boxcox passengers. And I'm going to see what was the optimal lambda, and I use this function. So boxcox passengers is going to output 2 things: transform data, optimal lambda. So I'm going to save both of them. And I can see the head of the data set and then visualize it just like previously. I want to visualize the boxcox version and what is the value of optimal value of lambda, right? So let's do that. Oops, let's see. The boxcox is not defined, so we didn't import it. Okay, so let's do this one again. Am I getting the same message? Yeah, float argument string. Yeah, we have to go ahead and make sure we have our index set up correctly. Airpass dot. What do we do? Index to timestamp, right? Timestamp. So this should do it. There you go. Okay, so it seems that the optimal lambda was 0.15, or to be exact, 0.1480. And this is going to give us the close, if I look at the distribution of the data, it's going to give us the closest one to the normal distribution. That's how we are defining the likelihood function, right? For those of you who are familiar with the maximum likelihood estimation. So we have to define a likelihood function and try to maximize that one, the log version of that one. This is exactly what SciPy is doing behind the scene. All right, I don't want to get into the details, but basically, let me see, what is this? Yeah, so this is showing all of them side by side. But basically, this is the idea of transformation. This is original data. Probably if you want to do modeling, we would be better off doing modeling in this because the variance is more stable. The long-term predictions are going to be easier to do that. So there are different ways to fix this, right? I can use a model that is adding the components in a multiplicative way, or if I want to do it additive, I can transform the data depending on what you want. If you want to make sure that, for example, your performance metrics are interpretable. Imagine you're doing RMSE. If I do RMSE, the unit of RMSE here is going to be number of passengers. Here doesn't make any sense, right? So I lose that interpretability. Here is log passengers. Here's the square root of passengers. But again, here doesn't make any sense. Yeah, what does log passenger unit mean? That doesn't make any sense either. So again, if you want to keep it interpretable, you have to think of modeling differently. We're going to cover all these things later on. Don't worry about it. Okay, so the summary, we talk about this. So transformation in general is going to stabilize the variance. It's going to improve convergence, especially in deep learning and non-parametric machine learning models, right? Yeah, let's see. And it speed up the training and lead to better results. So that's obvious because on those models we are doing, let's say, gradient descents, and if the data is normalized, it's going to converge faster. It's not mandatory though. It's not mandatory for non-parametric models. For parametric models like classical linear models, yeah, probably we would be better off to do that. But for non-parametric models like deep learning and more advanced machine learning models, we don't need to do that. But it's beneficial simply because it's going to improve convergence when we're doing gradient descents or using different algorithms. All right, so the next one is ACF, PACF. So we talked about the theory of ACF, PACF previously, and in the theory lecture 1. Now let's see it in action, right? So you're gonna use a stats model. So from stats model graphics.tsa plots, we're gonna import plot ACF and plot PACF. And here's the documentation. You can click on it, and let me see. Yeah, there you go. So these are These are what you can put in for the features for when you're doing ACF and PACF, right? So feel free to read this documentation from stats model. And by the way, I didn't need to import stats model. I didn't need to install it because I already installed PyCaret, right? So if you install PyCaret, this stats model is already there. Okay, so let's go ahead and import them, and let's do, I don't know, let me see if it complained. No, it didn't. Yeah, it's okay. So this one can handle the index, right? Again, depending on the package, sometimes they have hard time handling the time index. So hopefully this is making more and more sense. It just needs a little bit of practice. So here we are plotting ACF and PACF. So we talked about the ACF, PACF for our well-behaved data set. I see this is scallop thing. So this is a sign of seasonality. I see a downward, the autocorrelations are decreasing consistently. So this is a sign of trend. And then we look at PACF to look at the net effect, the peer effect of, let's say, lag 1 controlling for all the other lags. And it seems that that's all we need. So maybe there's some seasonality component left over here. Every 12, 24, you'll see this a little spikes, but again, when we get to modeling, we talk about these things in more details. So we can do ACF, PACF for stock. Again, it seems that everything is reflected in yesterday's price, which makes sense. We talked about efficient market hypothesis and things like that in the theory lecture. So, all right, so this is how we can do ACF, PACF. Now let's move on to stationarity and differencing. So again, from lecture theory 1, we talked about stationarity. Why do we care about it? So let me actually show you the plots. Remember, guys, so imagine, so this one. Is this time series stationary? Obviously not, because there's an upward trend, the average is not constant, the variance maybe, the autocorrelation may change. So this is not a stationary. How about this one, our stock price? Is it a stationary or not a stationary? This is obviously not a stationary. So what is the problem when we want to forecast on a stationary? The problem is that if you want to do multi-horizon, let's say longer term forecast, if your data set is not a stationary, your forecasts are not stable. They're not going to be robust. So this is basically for longer term decision making, you need to make sure that your data set is stationary. And on top of that, some of our classical models are built based on the assumption of a stationarity, like ARIMA. So we have to make sure that if you want to pass the data to ARIMA, you need to make it stationary. That's the I component in ARIMA, by the way. Again, we're going to cover these things. But be careful. For example, if you're doing machine learning, or if you're doing deep learning or sequence modeling for time series, you don't need to necessarily make it a stationary. This is just, it doesn't hurt. So as long as it doesn't hurt, it's going to help you to get a more stable, longer term forecast. For one step ahead, for some cases, honestly, it really doesn't matter, especially if your model can handle non-stationary data, like neural networks. Yeah. Okay. So we know the concept of stationarity, and one of the remedies to make a non-stationary data stationary is differencing. But first, we need to figure out if a data set is a stationary or not. And one of the most commonly used test statistics for basically detecting if the time series is stationary or not is augmented decay Fuller, or ADF for short. ADF test is a statistical test used to check for stationarity. So basically the null hypothesis is that the time series is non-stationary. So you want to reject that null. So you want to get a small p-value. So that's what you want to get. If you get a small p-value, so you reject the null, you reject the non-stationary, and your data set is stationary. The theory behind it is not that complicated. I encourage you to just Google it or just use ChatGPT to educate yourself about the theory. There's a simple econometric model setup that we assume that there's a unit root, and then we're going to test if one of the coefficients is equal to 0 or not. So that's, again, the theory is pretty straightforward. And the solution is differencing. So let's go ahead and use augmented decay Fuller, ADF. So this is AD Fuller function or method from stats tools, from stats model module. Okay, so if I run this basically AD Fuller and then air pass passengers, the output is not it's not very informative, right? So it's 1, 2, 3, 4, and a dictionary. So there's a NumPy series and a dictionary in the series, and probably we cannot understand it clearly. So if you read the documentation, and then you will realize that, okay, what is the first number? What is the second number? What is the third number? So I went ahead and created a function for you. I call it ADF test, and then make it more interpretable. So let me actually run it, and then we can interpret it together. So the output of this function is something like this. Basically, again, nothing fancy here. If you run this, if you're familiar with these numbers, you can already read them, and you know that, okay, this is p-value is super large, so we failed to reject non-stationary. So this data set is non-stationary. But if you want to write a report, or if you want to give it more context, you have to make it nicer. And honestly, you can say copy and paste this to ChatGPT. Say, hey, how can I make it nicer? Create an ADF test function for me, and then add some context to that. Okay, so it will give you something like this. And we are going to save the results of this AD Fuller test. And then these are the labels. And look at that. Here's a list of 4 things. The 4th one is a dictionary. Inside that dictionary, we are doing a for loop. And this is critical value, key items, and etc. Right? Yeah, key value. So again, this should be pretty straightforward. And actually, it makes it more interpretable. It says that if the p-value is less than 5%, the series is stationary. If it is greater than 5%, it's not a stationary, right? Again, this 5%, you can change it to whatever you want. You can make it a function. You can make it, for example, alpha, and pass the alpha here in one of the inputs of the function as well. Okay, it should be pretty straightforward. So if I use this ADF test and pass the Apple data to that, I can add a title. So here's the results. So it seems that the p-value for, what is this one? For airline passenger is very large. It's not a stationary, obviously, because it was an upward trend, right? So obviously the airline passenger that goes up like this is clearly non-stationary, right? And then the p-value for a stock price stationarity was smaller than that, but it was a large number, which is 29. So this one is also still clearly non-stationary. Okay, so how can we fix it? So one way to do that is just differencing. So I'm going to go ahead and create a new variable, call it passenger diff, and use the diff function. Okay. So if I do diff, open close bracket, by default it's going to use 1. So it's going to say y minus yt minus y2 minus 1. So this is differencing 1. It's as if I create a lag value by using a shift function and then simply subtract them from each other. But I can do it directly. Okay. So there you go. So this is our passenger difference. Passenger difference. Obviously, the first one is going to be an A. The second one is this. 118 minus 112, so it's 6. 132 minus 118, 14. 129 minus 132, minus 3, and etc. So this is a diff value. Now we can go ahead and visualize that. I think it's going to complain again. Yeah, there you go, because just like previous one, I'm going to make sure that I fix these things and then push it to repository. So let's do air pass index to timestamp. Let's see. Yep, there we go. So here is the, look at that. Here is the difference version of airline passenger. This is how the data is going to look like. Obviously, there is a still increase in variance, right? So maybe I should have done differencing to log passengers, right? Or maybe I should have done differencing to boxcox transformation, right? These are all possibilities. So we can go ahead and do that. So here it seems that it is barely stationary because the p-value is just 5.4%, right? It is, so this one is still, I can say, yeah, still non-stationary simply because the variance is increasing. So maybe we should have done this differencing to boxcox transformation. So I'm going to go ahead and create boxcox passenger difference and repeat the exact same thing. We'll make sure that, let me just copy paste. The index is correct. Let's do here. All right. So look at that. This is more stationary. So if I apply the differencing to boxcox, so visually as well, it is more stationary. If I compare this one with this one. So this is clearly telling me that the variance is increasing. So it's going to be non-stationary, but this is stationary. But look at the p-value, it's 4.8. Again, there is some seasonality, clear seasonality component in it, so that's why it's still not 100% stationary. So if we, again, these are all relative, right? If you do the same exercise, the differencing exercise for stock price, you will see, look at that. So this is your stock price, right? Clearly it's not a stationary. The ADF p-value was almost 30%. So we failed to reject non-stationarity. But if I go ahead and difference this, remember, when I look at the ACF, PACF, when I controlled for lag 1, then nothing was left over. Look at that. So when I control for lag 1, it seems that everything is reflected in yesterday's price. So when I do differencing, probably it will remain some noise, right? So let's see if that's the case. So I'm going to do a simple differencing for Apple stock price close and then see how it looks. There you go. Look at that. The p-value is almost 0. So we strongly reject the idea of non-stationarity. So this is a stationary. Again, in stock market context, we see some heteroscedasticity here, and then we have to do some specific modelings to handle that one as well. But that's beyond the scope of this notebook. But at least this is a stationary. Again, so just remember, by performing the ADF test, we can determine whether our time series is a stationary or not. If it is not a stationary, we apply differencing to transform it into a stationary series. This transformation is essential for making reliable long-term predictions and for the proper functioning of many time series models, right? It's not mandatory for many models. For example, for our let's say decision tree base, let's say XGBoost, or for our RNN or CNN models for time series forecasting, we don't need to make a data set stationary. But again, if you want to do long-term forecasting, it makes your forecast more stable. All right. So the next topic is seasonal decomposition. So we talked about decomposition in lecture theory 1. We said that you can decompose a time series into its components, trend, seasonality, and whatever is left over. This decomposition is going to help us understanding the underlying patterns in the data, which is useful for modeling and forecasting. Remember, again, guys, I hope you are watching these videos back to back. You have to have watched module 1 when I go over modeling time series from scratch. We decompose the time series and we want to put those elements together in a linear or nonlinear fashion, or in an additive or multiplicative manner. So that's where this decomposition is going to help. If you want to build those models from scratch, if you have a complex non-parametric, recurrent neural network, basically this decomposition may not help unless you want to add some engineered features, right? These things that I'm saying right now, it's going to make a lot more sense by the end of the semester. So don't get overwhelmed right now. Today's session is just making sure you can do these simple operations in Python and you can handle time series data. So that's the idea. I'm going to repeat myself again and again and again during the semester, during this course. So I'm going to go ahead and import seasonal decompose. And as you can see, we're doing all these things from stats model. And PyCaret also can do these things using stats model. We're going to see how PyCaret does it later on. All right, so seasonal decompose, you just have to say, just use this function. You can check the documentation as well. Use this function, pass your data set, and the model is additive. So let's visualize it. Basically, if I do results airpass.plot, it's going to show me everything. Again, so interesting. So sometimes it complains, sometimes it doesn't, as you can see, right? So that depends on how, for example, the authors of this method or function was expecting the time index to be, right? So we need to fix it. So here again, this seasonal decompose is expecting a timestamp, basically date time index, but we are passing frequency. Again, remember guys, at the beginning of this notebook, we changed this frequency, we specified the frequency because later on in the course, we were doing PyCaret. PyCaret is expecting frequency. But when you're doing visualization, many packages just don't want it to be like that. They just want it to be timestamp. So we need to fix it. So how do we do that? Just like I can go ahead and create a temporary, I don't know, data. I can call it temp air pass, and create a copy of air. This is just for visualization, right? And look at that. My GitHub Copilot is already figuring it out. So when I just press enter here, the GitHub Copilot is generating something for me to suggest, and what is it doing? It says, okay, change the index to timestamp. So this should work, right? And now if I run this, it should work. Okay. Oh, I need to change this one. So temporary error. So there you go. This should work. There you go. And yeah, so that's the seasonal decomposition, right? This is the original data. This is a trend component, seasonal component. Whatever is left over is the residual. And obviously there's some clear pattern in residual. So this is not a good residual. So it means that this decomposition, we are not completely breaking down the time series into its components. There's something left over. So maybe if I change the additive to multiplicative, and make sure that, so this increase in variance is taken care of. Let's see how it looks like. Yeah, this looks better, and obviously it's going to be 1 because we're multiplying these residuals to this seasonality, to this trend, right? Well, actually we're adding trend and seasonality and multiply it by this, so it cannot be 0. It should be around 1. Again, these are, if you can add these components to each other in an additive way or multiplicative way, and multiplicative apply to the residual component. Yeah, so we can do the same for stock. So if I run this thing for our Apple close price, and as you can see, it seems that this is original data, this is trend, and it seems that they're basically the same because look at the magnitude of seasonality. It's nothing, right? 0.1 minus 0.1. So this is basically the data, and this makes sense. There's no daily seasonality in stock price, and everything is here. So whatever model you have, it better be good at predicting trends and cycles, which is combined together. By the way, trend and cycles are combined together. We call it trend, and seasonality is regular ups and downs. Cycle is irregular ups and downs, right? For example, business cycles, financial cycles. And the residuals looks like this. Okay, so again, the summary for this section was seasonal decomposition. We applied to airline, passenger, and Apple stock price, and we use seasonal decompose function from stats model. By decomposing the time series into trend, seasonality, and residual components, we can better understand the underlying patterns and behavior in the data. This decomposition is crucial steps in time series analysis, helping in both the interpretation and modeling of the data. All right, the next one is, which is the last one, is our benchmarks. So what are the benchmarks for our forecasting models? Okay, let's look into our benchmarking forecasting models, right? So remember, are we talking about multi-horizon benchmarks or one step ahead benchmarks, right? So actually, let me go back and show you something. So if you go to the module 1, I want to show you what we're talking about, the PDF, and we talked about benchmarks, right? So if you scroll down and bring the benchmarks, we talked about 4 of them, right? Naive forecaster, seasonal naive forecaster, mean, and, well, there you go, mean and drift method, right? So these are the benchmarks. We said either for, so this is what I'm going to replicate for you now. So this is where I'm going to show you the code. So the simple average is basically, we have to split the data into train and test first. So I'm going to say the last 24 month of observations are tests, and the first one, 122, I think, is the train. And we want to do a multi-horizon. Our multi-horizon is 24 month, right? Benchmark. So we can use a simple average. Simple average of the training data is this. This is a simple average. Then we can do drift method. Basically, look at the starting point, the ending point, connect them and interpolate them. We can look at the naive forecaster. So I'm going to use, for the entire 24 observations, I'm going to use the last seen data in the train set, which is this value. and we can do seasonal naive. Seasonal naive is that use the past January for the next January, use the past February for the next February, and it's going to repeat itself. Look at the green one. It's going to repeat itself for 12 months. So we're going to do this. We're going to do this in Python now. And remember, this is multi-horizon. If I want to do one step ahead benchmark, so we're going to do naive forecaster, which is one step ahead naive forecaster. Basically, we're shifting everything by one step, right? So today's price is tomorrow's forecast. So that's actually what we're going to do. So let's do it in Python. So let me remind you basically here what I'm doing. And actually, we're going to do something like this again and again when we want to split the data into train and test. So the train says that airline passengers, all the data except the last 24 observations. The test set is the last 24 observations. And let's plot them. Sorry, I need to fix this. So let me pause the video and fix the rest of the code. So you get the idea. I fixed a bunch of these things on the fly, so you should be quite comfortable with that. So I have to say train.index to timestamp. I don't know if it has S or not. And let's do the same thing for my test set. It should work. Obviously we need to change it to test. Okay, so let me pause the video and then see if there's a typo. What am I doing wrong? Okay, obviously there was an extra S here. And there you go. So this is your train and test set. Okay, so train and test set, then we need to create those benchmarks. So you know the theory of those benchmarks. You can go ahead and use ChatGPT and help you write the code, but the code is pretty intuitive. So starting with naive forecaster. So I'm going to go ahead and create something. And remember, you want to make predictions for the test set, right? So my y hat naive is going to be everything from the test set, but I'm going to add a column called naive. And it says, take the last observations from the train index, use it, and obviously the passengers, use it for all the future forecasts. So basically take this number. Hopefully you see my cursor. Take this number. This is going to be your forecast for all these 24 observations. This is your naive. Okay. The next one is seasonal naive, right? So seasonal naive, you want to say, what is your seasonality? You have 12 months, right? So the period is 12. Then we're going to say, okay, so take the past 12 observations from the train data set and then do this to that. So this is a new column called snaive. Do this. We're going to use tile function, and basically we're going to say, for example, use January for next January, February for next February. So this is what this code is doing for us, right? And so this is going to be your seasonal naive. Again, just copy and paste this code. Oops, sorry. Copy and paste it to ChatGPT and ask it to explain it to you step by step. This should be pretty straightforward. And what is the average? The average y hat mean is simply the average of the passenger data in train sets. What is the drift method? The same story. The drift method is, remember, let me actually pull it up. I need to somehow find the slope and then add it for each time step into the future, right? So how do I do the slope? So this is what we're doing. We're going to say the drift method. The drift. What is the drift? It says that take basically this is the very last one, the very last observation in the train set, minus the very first observation in the train set. Look at that. The very last observation in the train set, the very first observation in the train set, and then subtract them, divide by the number of steps in between, it's going to give you the slope, right? So divided by the number of periods, it's going to give you the slope. And then for your forecast into the next 24 months, you need to basically use a least comprehension and do it one by one, right? So let's say this is exactly what we're doing. For this one, use this index, multiply it by drift, and add 1 to that. So this is exactly what we're doing. See? Use the past observation, add 1 index to that, multiply it by drift for these i's. I go through the length of test. Again, don't get lost in technicalities here. And The point is that all these things can be generated with ChatGPT. And on top of that, if you're doing PyCaret is going to do this automatically for us. So my message to you is that don't get overwhelmed. Of course, learn how to read the code, learn how to understand the code. I don't want you to be a copy and paster, because if you just copy and paste, debugging ChatGPT's code is going to take you more time. So learn these things from scratch. And at least for a while, I think for the next couple of years, it will be like this until the ChatGPT is so good, or any other LLM model is so good that you just need to just communicate with them in simple English or any other language, and it's going to do the job for you. But until then, I think debugging ChatGPT's code right now is a skill, and so that's why you should learn these things from scratch. But at the same time, don't get overwhelmed. Don't get overwhelmed by the amount of code you see. This is all generated with AI. So your job is to understand the theory deeply. So let me run this, fingers crossed we don't get an error, but I think we're going to get, because the index needs to be fixed, but we'll see. There we go, same thing. So we need to fix those indices. Let's see. Yep, let me go ahead and fix these problems. All right, actually, I fixed the code. Well, the problem was the same. You have to make sure that these indices are to timestamp. And for this one, because there's so many stuff going on here, and I want to show you an example how we can just fix it with something like ChatGPT or Google Gemini. And let me actually show you what prompt did I use. So basically, I copied the entire thing. And obviously I was communicating with Gemini when I was putting together this file, so it's already aware of what problems did I have. Let me actually try to pull it up. There you go. So here, and I said, let's see. Oh, there you go. So this is the prompt that I gave it. So I'm getting the same problem here, and I copy paste the entire code. And then I pasted the error as well. And this is the output of the Google Gemini. ChatGPT can do the same as well. So it says, hey, that's a problem because you're giving it period index. We're not surprised. We have seen this problem many times before. So as you can see, for visualization, it seems that if you want to do some simple pandas visualization, it must be the date time, right? But if you want to do PyCaret, it's going to use period. So because we're doing modeling most in PyCaret, that's why I wanted to show you. And again, that was a good exercise. It shows you that there's a difference between how different packages are handling time series index, right? And now see how it fixed it. It says use your existing code and you need to add this. Ensure index types are correct. So I'm going to go ahead and copy this one and paste it here before doing the visualization. So again, nothing fancy here. We're changing the index to timestamp again for your naive forecaster, seasonal naive, mean, and drift. And then this should work now. Let's see. Okay, it's working. All right, so that was pretty much it for multiple step ahead. And we're gonna do the same thing for one step ahead. And again, we need to, let's see. Yeah, our train index is fixed now. Test index is fixed. So let's see, maybe there's a little bit of fix here. Let me see. There you go, it works here because we already fixed the train and test index. And all right, so what is the one step ahead benchmark? The one step ahead benchmark, it's super simple. It says, we call it y-hat naive, let's say corrected, naive one step. And whatever it is, this is simply shifting your airline passenger one step ahead, one step forward, right? So whatever happens today is your prediction for tomorrow. So it is as if you're shifting everything one step forward for predictions. So this is why it's exactly the same as the gray line, but one step ahead forward. So this is, if your model can output something like this in the test set, it's a good model. For a well-behaved data set like this, it's super simple to output this dash gray line. But for stock price, you will see it's sometimes super complicated and super hard to output this red dash line. So one last exercise for you. Okay, I don't have it here. Okay, I don't know why it didn't show up here. Oh, because I ran the code entirely. So I'm gonna fix this for you. I will show you the images, and then you're supposed to replicate those ones, right? So basically, I want you to repeat this exercise multi-step ahead and one step ahead for your stock price. Well, actually, we have it here. Let's see. I'm gonna put the link there. So where did we put it? We put it somewhere here. No, not there. You go. It should be here. There you go. Here. I want you to replicate this for Apple's stock price. We have the stock price. Don't worry about. I think the time in this is correct because the Yahoo Finance is by default daytime, and we didn't need to. We specified the frequency to days, and then we didn't need to fix the code. So let's see if you can replicate this. So that's your exercise. I think, yeah, that was pretty much it. You are now ready to dive deep into the future modules of the course, which is, let me actually walk you through these ones. So next time we're going to do exponential smoothing. These are methods. On top of those methods, we're going to create models. We call it ETS. And then we're going to do ARIMA, ML, deep neural networks, sequence models, profit, and neural profit. All right, that was pretty much it. Until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.